Hi, guys. Okay, I think before we get started, I want to call your attention to a couple things. I took a look at the survey that you guys filled out and posted. Let's see, oops, some of the things, sorry. Some of the things I want to talk about. Sorry, I'm letting people into the class. So I posted solutions for the homework problems. I created, if you look on our modules page, right, at the very top, so we go by week, but at the very top before all the weeks start, I created a module called Homework Solutions. I posted the solutions for all of Chapter 1 and for Chapter 2 up until 2.3, so you've handed those in already. I have not been posting the homework solutions so far because we have this rolling window, right, of you can resubmit your homework problems for more points back. And I want you to have a chance to try out the homework problems, you know, see if you can learn the material. But I've always planned on posting solutions before the midterm exam so that you can compare, because, you know, I don't grade the homework for correctness, I grade it for completion, essentially for effort. So I put up these old solutions. So absolutely you can go back and look at all of those old stuff. And if you have like missing homework problems that you want to get points back on, now you have the answers, you can fill those out and resubmit them. You know, let me know so that I can go back through and then, you know, take a look at them. What else? Yeah, so they're up there. I'll post the rest of the homework solutions when we get closer to the exam. So the exam is actually next week on the 22nd. It starts on the 22nd. So we'll have that 24-hour availability window for our exams again. And we'll talk about that a little bit towards the end of class as well. But anyway, so the rest of the Chapter 2 material that will be on the exam, I'll probably post it, you know, like Tuesday or Wednesday of next week. So I want you to have a chance to work it through and try it before I actually post the solutions to that. So you can see most of the homework solutions up on our modules page. You guys asked about quiz solutions, and that's a great idea. I need to scan in my solution sets and then get those up online for you, and I'll have those you know, within the next day or so. Let's see, so we have, it's a short week today. This week we've got today and tomorrow's classes. We do have a quiz tomorrow. Sorry about that. It's kind of in our schedule. So we have a quiz tomorrow, but that quiz is on Chapter 2.4 and 2.5 only. So the stuff that we're covering today, tomorrow, and Monday will be on the exam, but it won't be on a quiz. You can take a look at those. Let's see what else. Yeah, so I think what I'll do today, what I'd like to do is, we have new material to cover. That's Chapter 2.6. If I'd like to lecture about it, and then work through the lecture examples. And then at the end of class, like the last, you know, 10, 15 minutes or so, then I'll open it up for questions on the homework, okay, so that we're not rushed and I can kind of gauge where we're at a little bit better. So save your questions for homework until the end of class, and then we'll cover them. And in the meantime, we're going to talk about Chapter 2.6. Okay, so I'll send an announcement later today, kind of summarizing the stuff that I just said. Also, after I've had a chance to post like lecture examples and lecture videos and stuff, I'll send out an announcement telling you again where things are at, where you can find stuff. But take a look on our modules page and you should be able to find the homework solutions there. Okay. Oh, and I also changed, I think that I had up originally that Chapter 2.6 was due tomorrow. We're doing 2.6 right now, so don't sweat it. 2.6 is due next week. Okay, so the only things that are due tomorrow for homework are 2.4 and 2.5. And those are the things that we're going to have our quiz on. I think that our quiz page now, the quiz header probably says like what chapters are going to be on there, so you can follow that a little bit better. Okay, I know that was a lot of information to take in. If I talk too fast to trying to get it out the door here, don't worry, I'm going to send it out in an announcement later today so that you'll have it in writing that you can reference later. Okay, let's go ahead and talk about Chapter 2.6. Okay, so we're talking about general logarithm and exponential functions. Okay, so we've been actually kind of dancing around this topic a little bit as we've been going, right? We've been talking about mostly like natural log as our logarithm base e, and e to the x as our exponential function base e. We've been talking about that. Every now and then I'll throw in, this is the generic base or whatever. But now we're going to talk about it, specifically in chapter 2.6. So if we think about b to the r as an exponential function, let's write it down. So base is equal to b, and then our exponent is equal to r. This is actually our variable. Okay. This is different than like a polynomial where I have our variable raised to a number. This is a number raised to a variable. Okay. So we can think about this b to the x in terms of x. So if I write this in terms of I'm going to write e to the ln of b. That whole thing is raised to the rth power, which looks like e to the r ln of b because I'm multiplying the exponents together. Okay, so in this case, b is equal to e. Okay, so now our book actually has a nice, sort of semi-proofs or proofs about how this is going to be. I tend not to cover proofs in the class because the book covers it nicely, and our final exam and our midterm exam, and what you're expected to take out of the class is essentially like a set of tools, a toolkit to help you analyze and think about and solve problems. Okay, so that's why we focus more on the hands-on work, okay, and like the toolkits and how we're going to actually work through these problems. But if you want to see the proofs and where all this stuff comes from and why and all that, I think our book does a pretty nice job of explaining stuff like that. So you can take a look at our book because I'm just kind of giving you the high level view of what this is here. Okay, so let's talk about a definition. DEFN, that's my abbreviation for definition. So if we've got b is greater than 0, our base is greater than 0, and our exponent is a real number. X is an element. It could be, right? Our exponent is a variable, x, but it's part of our real number. So we're not talking, in this class, we pretty much stay in the real domain. Okay, all this stuff has its own set of rules when you talk about imaginary exponents and imaginary bases, but this class is all in the real domain. So we're looking at b to the x as an exponential function, okay, how we're going to do it. So if I say, b to the x equals e to the x ln of b, we're looking at a domain of minus infinity to positive infinity, right? I can choose any x value that I want for my domain. We tend to say we don't want b equal to 1. It's not a domain restriction like it's going to give me a divide by 0 error or a radical of a negative number. It's just 1 raised to the x power is equal to 1. It's not very interesting. It's not an exponential function anymore. It's just a constant, right? So that's why we tend to avoid this as a base because it just reduces down to a constant term. So it's sort of a guideline as opposed to a domain restriction. When we think of our range, I think about your e to the x function, right? It doesn't, our y values, our output y values don't include 0, right? I mean, this isn't the closed bracket. It's asymptotic as we head towards y equals 0, okay? So our function's going to cruise right along that y-axis, right? Y equals 0. It's never going to reach it. This is what we're looking at here. Okay, and then our generic function, how we write this, f of x is equal to c times e to the x, where c is some constant. Some constant term. Typically, when we talk about exponential functions, c ends up being like an initial value. We're going to do an example with this towards the end. We're going to talk about like a word problem where we have examples. All right, let's talk about some algebraic properties here. Some of this is review, but a theorem, THM, that's my abbreviation for theorem. Okay, so first off, we're going to say a is greater than 0, b is greater than 0, x and y are real numbers. Okay, so just set down some ground rules first. So our first algebraic property, b raised to the 0th power is equal to 1. Anything raised to the 0th power is equal to 1. b raised to the x plus y, right? This is sort of like we're talking about general rules for exponentials, exponents, b to the x times b to the y. We tend to do this in the reverse direction where we'll see things that have the same base Okay, 2 to the x times 2 to the y becomes 2 to the x plus y. Okay, or I could break this up like this. This is going to become important when I have functions, like when you take, like say for example, math 3081, probability and statistics, we're going to have e raised to the whole function, right? And I need to be able to break it apart into a product. So when I take the natural log, then everything breaks up into different pieces here. So this is one of our exponential rules. Oops, b to the minus x is 1 over b, the x power. Anything when I have a negative exponent, right, that's just like saying this needs to be on the other side of our dividing line, okay? And the same holds true if this was 1 over b to the minus x, that would be equal to b to the x. It's just kind of reminding you. B to the x raised to the y power. Okay, these are, remember, like kind of general rules for exponentials. Raised to the y power is the same thing as b to the x times y. Okay, so be careful, these are not the same thing, right? This is b to the x times y, b to the x times b to the y. So we're adding exponentials. This is, right, our general rule for exponents here, okay? I'm raising it to the y power, which basically means I'm multiplying. If you're not sure, if you can't remember what these things are, use an example like with a number. If I go 2 to the 3rd raised to the 4th power, right, that's like 2 raised to the 3 times 4 to the 12th power. You can do that out on your calculator, get a number, and see, you know, see what you get. Maybe you don't want to use such high numbers, but you can do numbers out on your calculator and prove to yourself that you had it right. ln b to the x is equal to x ln of b. We talked about this before in our properties of logs, right? This is our exponential property of log. A to the x times e to the x is equal to a times b raised to the x power. All right, so what this means, right, is be careful, it's not the same thing as this here, right? I have different bases, but I have the same exponent, so I can bring them together. So this is like 2 to the 3rd times 4 to the 3rd becomes 2 times 4 to the 3rd power, okay, which is different than what we have here. Okay, so just kind of keep in mind just our general rules for exponentials. Okay. Let's talk about our derivative. So if we talk about our derivative with our exponential functions, right? So again, I want to specify that b is greater than 0. So if I have b raised to the x power, and I want to take that derivative with respect to x now, right? So I'm looking at, remember how we talked about this before, I repeat my exponential, I take the natural log of the base, and then I do the chain rule. Okay, I'll just write this part here as our chain rule. That says, right, take the derivative of what's up there. Okay. 3 different pieces. Okay, we do this automatically with e to the x as a function. The natural log of e is equal to 1, so we don't even see it. Okay. All right. So I'm going to pull out my lecture examples page for 2.6. And I apologize. I think that there was some a glitch on the Canvas page. I like a week ago uploaded a whole bunch of files to Canvas to our modules page, like homeworks and lecture examples and all sorts of stuff. And then one of our students, one of our classmates, called my attention to it that there was no content in there, and there should have been, because it was listed as a file that had been uploaded. But it looked like, I know Canvas has been working on some bugs, like the math department's been telling us that Canvas has been working on trying to resolve a bunch of bugs, and I think maybe in the process of that they did something weird to the server. Anyway, so let me know if you go to download something and there's no content there, like there isn't a file uploaded, and I'll check it out immediately. So I apologize if you guys went to go take a look at things over the weekend and there wasn't a file there. But this is lecture examples 2.6. Which you should be able to get off of our modules page unless Canvas ate it. All right, so I want to calculate the derivative of natural log of 3 to the t plus 1. So first off, remember, I cannot distribute my natural log to all these terms inside. I can't do that. It's a natural log of this whole block. Okay, So I like to think of these using substitution of variables. It helps me kind of keep track of what I need to do. You don't have to. Okay, you could just jump right in and give the derivative, but it can help you keep track of what you need to be thinking about. So if that's the case, I'm going to think about this as a u. So u equals 3 to the t plus 1 makes my derivative, right? The plus 1, when I take that derivative, plus 1 goes away, it becomes a 0, right? Derivative of a constant term is 0. So let's take the derivative of 3 to the t. I repeat the exponential, take the natural log of the base, and I would say dt, but there is no term of dt is equal to 1, so I don't have to worry about it. So now when I go to write this, I say natural log of u. And I want to take that derivative. It's going to equal to 1 over u times du, right? That's my chain rule. Don't forget to substitute back. If you give this as your answer, it will be wrong because u is just a temporary variable. So I'm going to substitute back. So this becomes 1 over 3 to the t plus 1 times 3 to the t ln, oops, this is ln of b. Sorry, I wrote ln of b. Ln of 3. Ln of 3. Ln of 3. Okay, and I can, put it all together into one fraction, or I can just leave it like this. It's fine. Same thing. Okay. You could have just jumped right to this. It would have been fine, right? This is like part of our chain rule portion. Okay. I like the substitution of variables because it helps me keep track of things. Okay. All right. So we want to calculate this derivative. So to do that, I need to be thinking of the product rule. Right? Why am I thinking product rule? Because I've got an x times 2 to the x. I've got two functions that I need to be worrying about. This is my product rule. It says first times the derivative of the second plus the second times the derivative of the first, or vice versa. You're adding, so it doesn't matter what order you do. Okay, so first x times the derivative of the second. Remember, I repeat the exponential, take the natural log of the base, and I go dx. dx is equal to 1. Plus the second to the x times the derivative of the first. I'll put the 1 in there so that you know I'm taking the derivative of that first term. And now I can, I can rearrange this. Looks like I can factor out a 2 to the x on each of these here. So I'll go 2 to the x. This is going to be x ln of 2 plus 1. I could have left it like that. They were both fine as answers. When in doubt, just leave it. Okay, because if you make a mistake when you simplify it, then you have to take off points, and that's painful. Okay. Yes, I'll have this here. All right. So let's talk about another definition. Okay, so if I say my b is greater than 0, my base is greater than 0. So let's spell it out. So if b is equal to 1, it's not a problem, but b to the x is equal to 1 to the x, which is equal to 1. So it's not really an exponential function anymore. So that's why we typically say we're not going to have b equal to 1 because just y equals 1, just a straight line. 2, if b is greater than 1, then b to the x is strictly increasing. And our function looks like this. So I'll just call it, for example, 2 to the x. Right, and I'm just going to draw in this little invisible horizontal asymptote. You don't have to draw that in, but what that means, right, is that my function's never going to reach y equals 0. Okay, and this is also concave. Oh. Okay. If b, I'm going to write, let's see, if b is between 0 and 1. So it's a fraction, right? And b to the x is decreasing. Okay. And it's going to look like let's call it 1/2 power, just as an example. Then I still have my asymptote line right there. Oops. Okay. Okay. Just as a way of thinking about things. So our example 3 is a word problem, and it's maybe you kind of saw some stuff like this when you were in high school, but let's go back and review. So example 3 says, if a patient is given 250 micrograms of a drug, how long will it be before only 25 micrograms of the drug remains if it decays exponentially with a half-life? Half-life means it decreases by half every half-life time period. So there's a half-life of 36 hours, right? So I'm going to take notes here as I'm working. This is an important question, especially with drug metabolism, because it can give us a clue. Say, for example, if a person's taken like radioactive iodine, and we need to know how long. We set this 25 micrograms as a dose where, you know, it's kind of like a safe level where the person isn't exposing the people around them to any kind of radioactivity. So if you take a dose of radioactive iodine, how long before it gets down to this level where your body isn't giving off radioactivity anymore? Because they'll say after this amount of time, or between, you know, after you take this until this amount of time, you can't be near people. You can't like hug your pets, you can't hug your children, or, you know, be near your spouse or whatever, because you're going to be exposing them to radioactivity, right? So we need to have some kind of an idea of how long does it take for this drug to decay in terms of radioactivity, or how long does it take for the drug to be metabolized in your system, for example, because that will help us with dosing, right? So like after a certain period of time, when the dose gets down to a certain level, then we need to take another pill, say, for example, so that the dose is always maintained at a semi-constant level, okay, in the person's system. All right, so these are important questions that we need to think about, but let's take some notes about like what things mean, and then we'll start working through the problem. So a half-life means that the mass of the drug decays by half each time period, right? So that, for example, like if we start off with 250 micrograms of the drug, after, in this case, 36 hours, half will be left over, which means that we'll have half of 250, so 125 micrograms, right? Then after another 36 hours, we will have half of 125, 2.5 micrograms of the drug, right? We just keep cutting it in half. Every 36 hours, it cuts in half, right? 36 hours is a short time span, right? I mean, like you hear about these, you know, the nuclear particles have half-lives of millions of years. Like it takes like 1,000,000 years for it to reduce down to half. So this is 36 hours is short by comparison. All right, so let's set up our equation. Equation that we need to represent this, because we don't want to be sitting here forever trying to guess, like when will it actually be equal to this value, when will it be equal to that value. So the equation that we're going to represent this is, I'll call it f, you know, as a function of time, right? So t is time. My units for time are going to be set by my half-life, so this is in hours. Okay, this is equal to our initial value. How much did we start with? Well, we started with 250 micrograms. So the initial value um, 250 micrograms. The initial value also sets the units for our final value, right? So this is in micrograms. My final value is going to be in micrograms. So this is initial value times our base raised to some time period. In this case, it's going to be the time period divided by our half-life. Okay, so our base, like they told us, it decays, has a half-life. It cuts in half every time. So the base is 1/2. They said it decays exponentially with a third life. It cuts by thirds every time. But I mean, radioactivity is generally measured in half-life. So our base is half our t. This is the variable that we're solving for. And then our half-life, oops, I can spell half-life equals 36 hours. Now they gave us a final value, 25 micrograms. So my final value in this case, 25 micrograms. So I'm going to plug all these things in to my equation here, and then I'm going to solve for my t. Right, this kind of goes back to maybe some stuff that you covered in Algebra 2 or Pre-Calc, depending on where your school was. So let's plug things in. So f of t, we said, was 25 micrograms. My initial value was 250. My base was 1/2. T is the time at which I reach 25 micrograms. If this thing cuts in half every 36 hours. Okay, so now I need to solve for this. So the first thing I'm going to do is I'm going to get rid of, bring over all my numbers, have my exponentials, right? So this is going to be equal to 1/10. 25 divided by 250 is 1/10 equals 1/2 raised to the t over 36. And that's a 36. Now, if I take the natural log of both sides, I can get this t out of the exponent, right? So I'm going to by the way, you can take a log of any base, but you know, we basically focus on natural logs. So I'm going to take the natural log of 1/10 equals, remember our properties of logs, t over 36 times the natural log 1/2. Natural log of 1/2 is just a number, right? 36 is just a number. T is now outside of the exponent. So now I solve for t. I multiply by 36, I divide by natural log of 1/2, and I basically find that t is equal to 119.59 hours, which is approximately 4.98 days. Okay, you could have left it in hours or days. I mean, it kind of helps us conceptualize how long it's going to be. Okay, so this basically says, you know, after 5 days, right, we've gone from 250 micrograms to 25 micrograms if the drug decays with a half-life 36 hours. So it helps me find exactly the time at which I reach a point that I have specified as being, you know, my goal. Okay. Give me a minute to finish writing that. I'll scan these in later today and put it up online. Okay. Right. So here's another definition. So do you remember when we said, you know, e to the x and ln of x, that these are, ln is the natural log base e, right? So these two are inverse functions. Right, they're inverses of each other, right? We said that with e to the x. It's true for any base of our log. Okay, so I can say, so b is greater than 0, and we're going to say b is not equal to 1, right? Because it's not a log exponential function anymore. So base b and logarithm base b, which is written like log base b, are are inverse functions of each other. So I would say b to the x and log base b of x are inverses. Okay, so all I've done is I've said we've been using it with base e, right, our natural log and our exponential with base e. And now we're just going to say this applies to all exponential functions, okay? And then we're going to apply that to, maybe you remember a thing called change of base formula. We're going to use the change of base formula to help us come up with basically derivatives with any kind of base. Let's remember. Right, so our change of base formula, oops, sorry. Remember, it's like if I've got, I want to take log base b of some number u, I'll call it u, some function u. Basically what I'm going to do is I'm going to say, I'm going to convert it to a base that I know, that I like. Usually we go with base 10 or base e, right, natural log. Those are the most common ones, right? Log base a of my base b. So for example, using base e, which is our natural log, we would say log base b of u equals, right? I'm going to say the natural log of u all over the natural log of b. Okay. Now this, right? So say for example, just a quick example. Like if I wanted to go log base 3 of 6, right? So how I would do that, I'd plug this into here. I would say this is going to be natural log of 6 divided by the natural log of 3. These are all just numbers, right? And we needed this change of base formula because like our calculator actually uses the change of base formula when it provides us with these functions now. Like the calculators now, you can do like a log of any base. But what happened was they spent a lot of time, they calculated the bases, the logs and the exponential values for log base 10 and log base e, natural log. And so there were these log books. They were like huge, like books that took up shelves in the library, right? That you could go and say, okay, well, what's the natural log of some number and what's the natural log of some other number, and how am I going to figure out what's the natural log of all these numbers put together? And so now, like our calculator does it, but our calculator is using a change of base formula to make this happen. Okay, so we're going to exploit the change of base formula, right? Using natural logs to help us figure out like what's the derivative here. So I'm going to use this. Like if I have a derivative of some, this is like basically like an unknown base, like it's a kind of an unworkable base. I'm going to write this down in a light colored number. So b is an unworkable base. For whatever reason, it's not very workable. And then say natural log or base a right here is a workable. Okay, so we want to get it out of something that's harder to think about into something that I can, do on my calculator or do very easily. All right, so if I've got log base b of u, and I want to take that derivative, right, with respect to u, okay? So what that happens is, remember, we go, this is 1 over u. That's like, remember how we do that? We take our properties of logs, right? When I take that derivative, 1 over u times, right, this is going to be 1 over the natural log of b. This comes from my change of base formula here. So natural log of b is just a number, right? 3.2, 1.6, with some number, okay? Natural log of u is my function. And then don't forget your chain rule. The du is the chain rule. Okay, so I'm going to put this is kind of like our end goal here. Okay, what we're trying to do. For example, right, if I'm looking at example 4, now example 4, I can just jump, example 4, I can just jump right in and then go ahead and take it. But I'm going to do substitution, my u substitution, so that I can kind of keep track of things a little bit better. So I'm going to say u is equal to x squared plus 1. My du is equal to 2x. And I'm going to write this as log base 10 of u. And I want to find that derivative. Okay. So log base 10 is not so bad. I actually have a button on my calculator for it, but we want it to be in natural log form. So what I'm going to do is I'm going to say this is going to become 1 over u times 1 over the natural log of 10 times du, my chain rule. Okay, so let's see how I'm plugging. Now I need to substitute back. Okay, so this is going to give me 1 over u. So 1 over x squared plus 1 times 1 over ln of 10. This is just a number, right? I just leave it as ln of 10 though. You don't have to give me some number, times the du, which is 2x. And now, you know what? I'm just going to do that. I'm not going to try to be clever. I'm not going to try to combine ln of 10 and 2. Don't worry about it. Leave it like this, okay? Because this is your answer as the derivative, right, of the natural log base 10, I'm sorry, the log base 10 of x squared plus 1. Right? So I want to call your attention. We want to talk about the difference between the power rule and the exponential rule for derivatives. Okay. So let's remember, right? So let's talk about things in pieces. So first, our power rule. So the power rule we use like in a polynomial where I have, say, x to the a, right? Where x is my variable and a is a constant. Okay. And if I want to find that derivative, dx of x to the a, what I'm going to do is, right, I'm going to apply my power rule. So I bring down the a out front, and then I subtract 1 from that. And then I would do dx. I would, if there's some kind of a chain, other things. But this is my basic power rule right here. Okay. So this is like if I've got x squared and I want to find its derivative, right? We do this all the time. So bring down the 2 and I subtract 1. Right? So that's my power rule. Don't get that confused. My variable is in the base position, right? And I'm raising my variable up to some number, okay, as a power. Now, compare that with my exponential rule, right? Say, for example, how this looks different. I've got my number raised to the variable, right? Where x is our variable and a is a constant. That's our base, right? So now, if I want to find dx, a to the x power, right? I'm still doing it. I want to take the derivative with respect to x, but now x is in the exponent. I have to use my exponent rule, which means I repeat my exponent, right? I take the natural log of my base, and then I do dx, my chain rule. Okay? So be very careful. Don't get them confused. We're going to try to confuse you and trip you up, right? So you want to make sure that you recognize when you're dealing with a polynomial or some kind of like a power versus an exponential, okay? But take a look at example 5. That's a great example of trying to confuse you, okay? Example 5, if I look here, t to the pi. So this is, t is my variable, so I want to go dt. So with respect to t to the pi plus pi to the t, what is that derivative equal to? Okay, so that means I've got here t raised to some number. This is my power rule. I've got a number raised to my variable. This is my exponential rule. Okay, so now I have to take each piece and use the rule according to that piece. So now, right, when I go to do my power rule, I bring my exponent down out front, and I subtract 1 from my exponent. Plus my exponential rule, which is I repeat my exponential, I take the natural log of the base, and I do dt. In this case, my dt is equal to 1. So I can rewrite this as pi e pi minus 1 plus pi to the t times ln of pi. Okay, 1 was a power and 1 was an exponential function. Okay, be very careful. We're going to try to trick you, so make sure that you don't fall into the trap of thinking I'm going to do the power rule or something. Okay, be very careful that you're recognizing which is the base and which is our variable. Okay, last concept. Basically a shortcut version of our logarithmic differentiation, which I want to make sure that we go over some logarithmic differentiation problems from 2.5 homework, so that we make sure we have that whole concept down, because it's a really powerful technique, and it's going to pop up again and again on the midterm, on the final. So this is called the general, I'm sorry, my bad. This is the power exponential rule. And I'm going to put in parentheses, this is our shortcut using logarithmic differentiation. Okay, so it's our shortcut for that. So this is like basically saying if I have a function g of x and I raise g of x up to the power of f of x, so I've got a function raised to a function. Now, like if I said this is y equals that, right? So you can think, right, I can do logarithmic differentiation on this. I take the natural log of both sides, right, which is going to give me natural log of y. This is going to give me f of x times the natural log of g of x. And then if I go to take the derivative, I now have a product rule that I have to worry about. Okay, so that's why we're doing that. So let's specify that g of x and f of x are both differentiable independently. Okay, so now when I go to take this derivative, so y prime equals raised to the f of x power prime, like that. Okay, so I want to take that derivative. Now my shortcut using this power exponential rule. Okay, absolutely you can do logarithmic differentiations, but our shortcut says how we're going to do this is this. Do f of x, g of x, f of x minus 1 times g prime of x. This is our power rule part. This is our power rule, right? You can see, right, I'm doing that power rule. I'm bringing the exponent down out front. I'm subtracting 1 from my exponent, and then I do the chain rule here, okay? Plus, right, my exponential part is I repeat the exponential. I take the natural log of the base, and then I do the chain rule. This is my exponential rule. Okay. You can kind of see bits and pieces of where the logarithmic differentiation would be happening. Okay, like I said, this is a shortcut for the logarithmic differentiation. Okay, you can absolutely do logarithmic differentiation on something like this. Okay, but this can help you if you're just going to take a shortcut. But remember, if you're asked specifically to do logarithmic differentiation, do that. Okay, don't use the shortcut here. All right, so as an example, we're going to calculate the derivative of this function here. So I'm going to write down all my little bits and pieces. So my g of x is equal to x squared plus 5x plus 3. And I'm going to write down, I'm going to prefetch all this stuff. And my derivative is 2x plus 5. My f of x is the exponential function, exponent function, 7x minus 2. My derivative is equal to 7. Okay, let's write down what our formula is too. So then h prime is going to look like f of x, g of x raised to the f of x minus 1 times g prime of x. That's our power part. Plus, let's do the exponential part. G of x raised to the f of x times the natural log of the base times our chain rule, our exponential part. And we're adding this piece and that piece. Okay, so let's plug in what we have. So my h prime says f of x, 7x minus 2 times g of x, x squared plus 5x plus 3 raised to the f of x minus 1, 7x minus 2 minus 1 times g prime, 2x plus 5, plus my second bit, right? So this says, let's repeat the exponential, x squared plus 5x plus 3, right, raised to the 7x minus 2 power times the natural log of the base, natural log of x squared plus 5x plus 3 times f of x prime 7. Okay, it's a lot. Now I'm just gonna, you know, I could multiply these out and get another quadratic. All I'm gonna do is like kind of bring some of these things together. Technically I'm done, but let's do the 7x minus 2 minus 1 is gonna look like, let's bring this out here, 2x plus 5 7x minus 2 minus 1 is 7x minus 3. Okay. Plus, let's do that last bit down here. All I'm going to do is just move this around so that it's in front of that part here. So it's going to look like right here. It's going to look like x squared plus 5x plus 3 raised to the 7x minus 2 power times 7 natural log of x squared plus 5x plus 3. We put it out front here so we don't get it confused thinking it's part of our natural log. But then that's it. Okay, you can kind of see bits and pieces of where the logarithmic differentiation would come into play. Like I said, it's a shortcut. If you are asked to do logarithmic differentiation, do it, okay? And then don't do the shortcut. All right, so that's it for 2.6. We've got about 10, 15 minutes or so before the end of class, and I'd like to open it up for questions on the homework problems. What I'd like to do is to tell you, excuse me, my 8 o'clock class asked for certain homework problems, which I'm going to put online. I'll put online for our class too, but let me just tell you what homework problems those are going to be so that so I'm going to put these up online later today. So 2.4 question 40, 25 and 52, and 2.5 question 48. I'm going to put all those up online later. So if you have questions other than these, then I'll take those now. And if you guys have questions that I need to put up online that they didn't ask, then I will share those with them. You guys can put it in the chat if you want. You want to ask about. Let's I'll come back to question 2.3 in a minute. Let's do 2.4 first because that's what we have our quiz on tomorrow. The 2.3 homeworks are now up online. The solutions for that are up online. But give me just a sec. We'll go through all the 2.4 and 2.5 first, and then we'll come back to 2.3. Where am I? So 2.4 for 30. Okay, so the set of critical points. So let me get out my pen. This is chapter 2.4, question 30. Okay, so this is our set of critical points for the function f of x equals e to the g of x. Okay, so and we want critical points. Okay, so now for this, what we're looking at is basically looking at g of x because our e to the x function, right, is a constantly, it doesn't, it essentially asymptotes. So I'm looking at critical points of g of x as where the action is going to be taking place. So when I go to take the derivative of x, I'm going to look at e to the g of x times my chain rule, g prime of x equals 0. So this is the thing here that I'm going to be looking for where the critical points on g prime. Okay, so this is going to be true. G prime of x equals 0, right? Because e to the function isn't going to ever be able to reach 0, so it's only where g prime of x is going to be reaching 0. Right. And I think we weren't given, there's no function for g of x, so that's it. That's basically sort of like a theory question. If we were given an actual function for g of x, then I could actually jump in and give actual values for x, but in this case here, we're just doing it sort of abstractly. Okay, so that was 2.4, question 30. Okay, so 2.4, so question 30 was the question a lot of people were asking about. Let's see, and 34 and 39, sure. Question 34. So 34 looks like f of x equals e to the kx. And what is fn of x equal to? So this is like our derivative, our nth derivative, right? And so let's write that out. Nth derivative is what they're asking for. Okay, so how I want to think about it, I'm going to, if I'm not sure, I don't want to jump right into the nth part, but maybe I'll start thinking about like, what's my first derivative? So my first derivative is going to look like, I have e to the kx, right? And then I've got the chain rule, so I've got k times e to the kx, right? And then my second derivative, and I can get an infinite number of derivatives, right? Because e to the x is this special type of function where I have an infinite number of derivatives. So my second derivative, right, I've got the k from before, and I've got the k, this is my chain rule, e to the kx. And then, oh, look, I'm going to do my third derivative, k times k times k, e to the kx. The fourth derivative, you can imagine, it's going to be, I'm going to have 4k, so I'm going to go k to the fourth, e to the kx, right? So I'm not sure what the nth derivative is going to be when I first look at this problem, but by enumerating the first set, the first handful of derivative, I start to see a pattern. First derivative, I have 1k. Second derivative, I have 2. Third, we have 3. 4, we have 4. So that means most likely I can make a general statement. My nth derivative is going to have nk's kx. Okay, so when you're given a problem like this, we're kind of introducing calculus 2 types of questions. This is the kind of thing that you're going to do in calculus 2, where you come up with like the first handful of derivatives, right? Then you want to come up with some kind of formula to describe your nth derivative, right? So go ahead and enumerate the first handfuls till you start to see what the pattern is, and then it will help you think about it. For 39, I think, did we do, this is like our normal curve. I thought we put up 39. Did we put up 39 online already? I think we may have put up chapter 2.4, question 39. This is our normal curve. We may have put that up online already with our critical points and our inflection points for that. Is it online? Ready? I would check online for that already. I think we may already have it. If it's not, I can put it up there. I'll check. 2.4, question 39. I'm pretty sure that's there because I remember solving stuff like that. Yeah. Right. So 2.4, 39, 2.4, 42, and 43. Okay. So let me do this. The hyperbolic ones. So 2.4, 42. And 43 are both long, so I'm going to put those up. I'll put those up online later, okay, because they're just longer questions. Number 52. Yeah, and 52 is one of the ones that my 8 o'clock class asked about that I'm definitely putting up online for you already. I want to actually go over a problem from 2.5 that was a logarithmic differentiation problem, just so you guys can make sure that you have it. I don't see anybody asking about 2.5 here, so I'll choose one. So let's do for 2.5, and then I'll do question, like maybe question 17. This is 2.5, question 17. Okay, somebody's asking that. Excellent, great minds think alike. So 2.5, question 17, we're going to do y equals e to the 3x squared, 3x squared plus 2x plus 1 times radical x plus 1 all over 2x squared plus 5. We want to find the derivative, and we're told to use logarithmic differentiation. Okay. So the first thing I need to do is I need to take the log of both sides. It's going to give me natural log of y equals the natural log of this whole function right here. I'm not going to write it out just for time's sake. So I got the natural log of this, and then I'm going to take derivative both sides. So this function here is what's going to be in there. I'm going to take the derivative. Remember, I'm taking the natural log of both sides, which means I have to take the derivative of both sides. So derivative is going to be 1 over y. Don't forget your chain rule, because dy dx is what we're solving for. Equals now, right? When I take the ln, remember the ln of e to the 3x squared plus 2x plus 1. When I take the ln of that, right, these are inverse functions. So what I'm left with is I've got 3x squared plus 2x plus 1. Let's do this. We're going to take the derivative dx. I'll write out what it looks like. Plus 1/2 ln x plus 1. Minus ln 2x squared plus 5. And I'm taking the derivative of that whole piece right there. So that's going to look like, this is 1 over y dy dx. So now the derivative, right, I'm just going to take the derivative of that, the derivative of that, and the derivative of that. Now this is a negative, this I'm subtracting. That's because of my, it was in the denominator. So that's part of one of our rules of exponents, our quotient rule. All right, so the derivative of my polynomial is going to look like 6x plus 2 plus the 1/2 gets carried out. Take the derivative 1 over what's inside. My chain rule says the derivative of here is just 1, right? Minus, okay, I've got this. So this is going to be 1 over 2x squared plus 5 times my chain rule, x. Okay. Now, I have to solve for dy dx. I have to multiply both sides by y. So my dy dx equals y times, and I'm going to clean this up a little bit, 6x plus 2 plus 1 over 2x plus 1, right? That's 1/2 times that fraction minus, I'll put the 4x all over 2x squared plus 5. But I don't want to leave this with a y variable. I have to substitute my function back into place. So dy dx looks like, so e to the 3x squared plus 2x plus 1 times radical x plus 1 all over 2x squared plus 5 times 6x plus 2 plus 1 minus 4x 2x squared plus 5 there. Now, don't be tempted to leave the y here. You want to write it all out. This is our final answer right here. And then don't worry about multiplying things through. Leave it. You're done. Okay. All right. Let's see. I think that was a good one. I think I can do one more. I can do question 21. I'll leave that for just a second for you guys to finish writing it. Okay, let me do the last problem here. I'll just choose. I'm choosing question 21. This is 2.5, question 21. So g of x equals x to the x. I usually just then substitute it to be y, just because I know I have to do logarithmic differentiation. So I'm going to say the natural log of y equals the natural log of x to the x, which is going to make it x ln of x. So when I go to do the derivative, I have to be thinking product rule. Right, when I want to take this derivative here. So now take the derivative both sides, 1 over y times y dx, product rule. So the first times the derivative of the second, right, plus the second times the derivative of the first. Right, so this is equal to 1 plus ln of x. Now I have to solve for dy dx. So dy dx equals y times 1 plus ln of x. Now I have to substitute back in, which is going to equal to x to the x times 1 plus ln of x. And you can just leave it, y dx. Okay. There. How's that? That's 21. Okay, guys. And if you have any other questions you want to talk about, you can come to office hours, okay, and then we can talk about it in private there. Okay, guys. All right. Have a great day, and I'll see you guys tomorrow.
Thank you. Have a good day.
Bye-bye.
Thank you. Bye.
Bye. Take care.
Thank you.